Hello, everybody. Let's start our session of the webinar Energy Future, organized by Joint Innovation Center of Bulgarian Academy of Sciences. This is part of Balkan Med Innova Web School, and my team and myself, we are ready to start discussing the main topic, Energy Future. And more precisely, we'll focus our attention on the energy overview that will give you a chance to identify some opportunities for future innovative efforts or business activities that will help you to introduce some new energy sources into the business endeavor you're going to undertake in future. Energy future depends very much on the environment and environmental changes. And as you can see from the graph, these millions of metric tons of CO2 will go down, will decline steadily from 2020, from this year to 2050. It means that new energy sources should be identified and introduced into the economy, into the sector of technologies and business. Now let's start with very elementary information concerning energy. What is energy? You know, I mean, everybody knows that there is a law, named first law of thermodynamics. This is the law of conservation of energy, and this law of conservation of energy will give us a platform for identifying some business opportunities and for developing some new technological development. So energy can neither be created nor destroyed. It means it exists. The only thing that is happening with energy is that the transformation or the diversification of energy types. Energy can only be transformed. This is quite important from one state to another, and there are different types of energy, like mechanical work, thermal work, electrical work. That is well known worldwide, and even in high school, this is a topic of discussion and study. So the main question is how to convert energy and how to make it cleaner and more efficient and more eco-friendly and more friendly to the societies. So first, let's classify energy, and the typologies of energy could be based on two types of main energy sources: primary and secondary. The primary is the energy that's harvested directly from natural resources. There is an indicator of the usage of these natural resources of prime energy. This is total primary energy supply, TPES, that is giving you information about the level of usage of primary energy sources. Secondary energy is a carrier of energy such as electricity. So electricity is already a secondary energy. It's produced by conversion from primary energy sources, and it's evidently clear that secondary energy should be produced in different premises, like electric plants, suitable installation that can transform primary energy into electric energy, or fuels, and so on. So there is a term well known as primary energy flows. So what are flows, energy flows? These are natural processes with energy that can be extracted in order to be used. Energy flows are natural, or they come from Earth, or from sun, or from magnetic or heat, or solar energy, and so on. So the water also flowing downstream in a river is also a source of energy flow. Wind is evidently a flow, and we will emphasize this type of energy flows because they are clean first. Second, they are eco-friendly because they are clean, and third, they are very efficient and very effective. You can use photovoltaics and solar thermal stations in order to produce this energy flow from sun, or you can use hydropower, or you can use the power of waves and tides. So tidal power is also quite important energy flow. Same thing is true for geothermal power and so on. So Earth and sun, these are the main sources of energy flows. In what way you can use primary energy? Of course, they could be used in different way, but it's important to transform, to convert this primary energy into energy flow, or into secondary energy flow. So, for example, oil or gas into electricity. This is the way you can guarantee that consumers can use the primary energy in the form of gasoline or electricity. So it's important primary production of energy to be based on different forms of natural sources, and when natural sources are exploited, then fabrication of this energy will happen. So, for example, here is given one example. In coal mines, crude oil fields, and hydropower plants, there is such a transformation. Or you can take as an example biofuels and fabrication of biofuels. That is also a good example. Now you can see here all these energy sources, but classified from the viewpoint of their condition, or their physical condition. So crude oil, coal, natural gas, nuclear power, as well as geothermal energy, wind energy, solar energy. These are physical energy sources, or fuels that are based on physical energy sources. So the most popular and widely used, this is the crude oil as a naturally occurring source, but it's highly toxic, and these CO2 emissions are based on the burning of these sources, of this transform from crude oil fuels that are polluting the air and contaminating the soil. Even the way this crude oil will be transformed into gasoline, gas, and so on is also toxic, because you know that refineries they emit a lot of gases, a lot of emissions, CO2 emissions, and so on. Coal is also a physical energy source. So you've got different type of coals, so brownish and black sedimentary rocks. They are forms on the base of fossil plants. And you know very well that coal consists of carbon with various organic and some inorganic compounds in it. So coal is a conventional source, physical energy source, and it's already in the list of the biggest polluters worldwide. Natural gas is another mixture of hydrocarbon gases that occurs with petroleum deposits consisting primarily of the gas methane, and in the same way as oil, they are based on fossil fuel formation. So you've got a lot of sources of natural gas that are part of oil deposits. But gas, as you know, is the least harmful if you compare it with crude oil and coal. But although not too much polluting and contaminating, natural gas is also in a way contributing for CO2 emissions and for some environmental harmful effects or outcomes. Nuclear power is clean energy source, except if you cannot control the emissions. So when you are splitting atoms, this is called nuclear fission. If an emission of this contamination will be released into atmosphere, this is quite dangerous for population, because you know very well how dangerous was the accident in Chernobyl nuclear power station, and what was the effect on the population in Europe and so on. So, but nuclear power is based on the fission chain reaction, but there is another nuclear power reaction, that is the fusion. So you've got a more efficient way to produce nuclear power, and after the fission chain reaction will happen, you heat water, and as a result you produce electricity. Geothermal, they use the power, the heat coming from the volcanoes and different other thermal sources of water, springs and so on. Historically, geothermal energy extraction has been limited in the regions where there are such active volcanic activity, or near to the tectonic plates and the boundaries of these plates. So these regions are also well known as quite active from the viewpoint of earthquakes, and this activity, of course, is not very very desirable from people, because there is a natural fear from this tectonic catastrophic events that can happen. But the geothermal energy is quite a good source of energy, and should be used widely. Wind energy. Wind power is growing at the rate of 30% recently, average level of increase. A lot of stations, turbine technology are used quite largely, but these turbines, they are also dangerous for birds, and some propellers can kill birds, and not only in a way they are affecting dangerously the, these migrations of birds from one place to another. So there are also drawbacks from this source of energy technologies. Solar energy has been used by humans since the beginning of mankind, but nowadays solar energy is used quite actively. You know, these photovoltaic solar parks based on cells that are installed in different large areas, especially where the sun is actively used for generating energy. But solar energy being the most popular just now after the wind energy will be discussed later on again. Hydroelectric dams, they are used for producing electricity. This is the electricity that is produced by hydropower. Normally, the force of moving water from moving water from high elevation to low elevation because of gravity, the electricity will be produced. The turbines are used in order this electricity to be produced. Tidal hydropower is for regions where there are tides, and tidal hydropower is quite effective source of energy. When these pieces of equipment, they're reacting to the movement of the ocean water, and turbines are producing electricity, similar, of course, to hydroelectric dam production of energy. A wave hydropower, it uses the energy that is created by the motion of waves from fluctuation of water below, on the surface and below the surface. So waves are quite effective source of energy, and efficient source of energy should be used also widely. Radiant energy, the energy used for heating, and solar energy is also a source of radiant energy. So you heat the water, and in this way you facilitate the process of exploitation of some, let's say, swimming pools, or for households. It could be used in households. As you know, hot water is an essential element of every household consumption. Now, what are the energy systems of the future? This is the big question that we'll discuss just now. As you know, we are living in Industrial Revolution 4.0. Industrial Revolution 4.0 is based on Internet of Things, but not only. Our society is already part of the so-called sharing economy. Sharing economy, if you want to understand really what is the main example for such a sharing economy, these are these are activities like Airbnb, Uber, and other individual or collective business or oriented activities, you can find important implementation of sharing economy into the energy sector also, and more precisely, these prosumers are such a good example of how sharing economy can be part of the sharing economy of the energy systems. Prosumers, who are prosumers? Prosumers are individual or a group of people who are producing, not only consuming, but also producing energy. So let's say you are a household and you reside in a house. On the roof of the house, you install photovoltaic panels. You produce energy, you consume energy. During the summer, if you go on vacation, of course, you stop consume energy, electrical energy. That's why you can sell this energy to the operator or distributor, or so-called grid. You can branch your house to the grid, to the public grid, and this way you can start selling this energy to the energy operators. So a shared electricity future is, of course, still a future, but in all cases, this is not futuristic. It's something real. It will happen soon. As a matter of fact, our case study is based on this type of prosumers activity, as well as the way grids are functioning. Now, the sharing economy opportunities in electricity sector are quite enormous, quite large, quite numerous. Now we can share not only products, not only electricity, but also services. This is the future of so-called smart grids. You know that smart cities, they are based on existence of such smart elements, including IoT, iOS, but also smart grids. Energy efficiency is based on demand flexibility. If demand is flexible, no leaks of energy will happen, no losses of energy will happen. So distributed consumption is quite important to be based on such a smart grid concept. Now let's see what are the social dimensions of the energy system in the context of this collaborative and economy of shared consumption. So first, you know that classical way of organizing business activities is based on market-driven economy. So market-driven economy is a result of so-called industrial capitalism of the Industrial Revolution 1. After that, what happened is Industrial Revolution 2. We are in the Revolution 4. That is the revolution based on Internet of Things. But in what way the social aspects are changing during different stages of industrial development? Historically, the collaboration is the main characteristic of today, but it used not to be a main characteristic yesterday, because collaboration is based on the existence of so-called synergy effect. So if you know, presumably the term co-opetition when you cooperate and compete in the same time. So this is not a severe competition, it's a cooperation. In this way, competition will happen. But European Union, is very much oriented toward and analyzing the challenges of these social dimensions of energy system, and regulation and deregulation. This is what is important for the EU nowadays. Now, another source of modern, futuristic source of energy these are so-called biofuels, not because it's quite high-tech energy technology, but because this is quite friendly as far as the environmental effect is concerned. And all wastes existing in the agriculture and also in the waste depositing process, they are going to be used in order to produce these biofuels. You've got different types of biofuels, like bioalcohols produced. You can produce propanol and butanol, or commonly known ethanol, because ethanol is the main bioalcohol source of energy. Biodiesel is a vegetable oil or animal fat-based diesel fuel. It's used in many cases when you've got such wastes existing in the food processing industry. Biochar, this charcoal used as a soil amendment in this biochar is made from biomass via pyrolysis. Biogas, this is a byproduct from anaerobic digestion of organic waste streams as livestock farms, food processing plants, and so on, breweries, and so on. Solid waste, all these burning trash that exist in the waste deposit places, they could be usable from the viewpoint of energy production. Biomass, any organic matter, wood, crops, seaweed, animal waste that could be used in order to produce energy from this biomass. Landfill gases, we have already discussed about the possibility to use solid waste to produce energy, but you can use also the landfill gas. Landfills naturally exist around big cities, and you can use this landfill gas in order to produce energy, or biogases for the same purpose. Here you've got a list of the most important for nowadays energy sources. These are the energy sources not only of today but also of the future, because especially the first one is space-based solar power. You know very well that when you install some solar panels on the roofs, this is not enough to produce large quantities of energy. If you use land for this purpose, you will destroy the function of the land for producing agricultural products. That's why space-based solar power technologies are quite effective from the viewpoint of usage of so scarce land resources. So these are so-called space solar panels that are turning around the Earth in orbit. Human power, you know that there are some disco clubs with such fixed pieces of equipment that transform the energy of dancing people into electricity energy. That is quite funny example from the viewpoint of very industrialized types of technologies nowadays. But every single possibility in the field of using all sources of energy power should be used nowadays. Tidal power, we have discussed already. Hydrogen fuel cells, this is also a future. You know very well that many producers of cars in automotive industry, they are developing projects in the field of hydrogen fuel cells, and this is of course quite effective from the viewpoint of achievement the main goals in business, but also efficient from the viewpoint of cleanliness and efficiency. Geothermal heat, we have already discussed. Nuclear energy, solar windows and solar facades of buildings is the future. Algae is part of the most efficient sources for biofuels energy, wind energy, nuclear fusion, and so on. That's all for this theoretical part. Now we will continue with quite a good example coming from United Kingdom. This is the example of so-called smart grids. So my assistant here presented will try to get you acquainted with the case, and we'll study it. Thank you.
Hello, everyone. Can you hear me?
Yes, we can hear you well.
I would also like to thank you for joining us on today's webinar. Of course, we are going to continue talking about today's topic, which is energy future. But now we're not going to talk so theoretically, and we're going to specialize in a few specific cases. So going on to the next slide. So as you can see, this is a picture. This is a hint of what we're going to talk about after that. As you can see, this is a facility with solar panels, and today we're going to talk about how the different energy sources can benefit our communities. And moving on with the actual first case study. Microgrid provides resiliency hub with sustainable power to community. As you can see, excuse us just for a second. As you can see, here we provide you with a link with the full article. So you can, of course, after the presentation, you can click on it and read some more. So today we're going to cover this topic, and after that, we're going to be able to answer the following questions. What is the role of the microgrid in the community energy park for the improvement of energy efficiency management system in the North Bay community, as well as what type of renewable energy source is used there, and also what is the way that the microgrid in the community energy park is guaranteeing to users sustainable energy capturing and sustainable energy to capture and store. Moving on. So this is the actual backstory of the study case. When an ice storm hit Ontario, Canada in 2013, transmission lines were knocked down, leaving hundreds of thousands of residents without power for days. Without electricity, the communities within the province are at risk of being exposed to perilous temperatures. With climate change increasing the future prevalence of severe winter weather, North Bay Hydro Services sought to secure the warmth and safety of the North Bay community by improving power resiliency. The Ontario-based municipal utility affiliate decided to develop a microgrid that could island a group of buildings and shelter residents if a winter storm took out the power in the North Bay for days. It's called the Community Energy Park, and it is the first utility-scale advanced microgrid in Canada. The group of community-centric facilities include the YMCA Aquatic Center, the Memorial Garden Sports Arena, and the Thompson Park Sports Field. The microgrid had to be able to deliver power primarily generated by distributed energy resources, adapt to existing building infrastructures and electrical equipment, and of course operate independently of the main electrical grid during a sustained outage. Because the aquatic center and memorial gardens buildings would shelter thousands of residents from the community, the microgrid also had to supply enough electricity and heat during the entire time of the refuge. So to sum up this slide, climate change is even more prominent topic nowadays. So it's nowadays it's more difficult to how can I say this? Okay, moving on to the next slide, excuse me. The S&C solution to this problem. To accomplish these goals, Norway Hydro Services wanted to work with a company with strong microgrid experience that could help simplify the complexities of developing a microgrid and provide a turnkey solution. The utility affiliate ultimately chose S&C Electric Company. Norway Hydro Services project commenced with collaborations between S&C's microgrid front-end designers and engineers and Norway Hydro Services team. During the design phase, S&C performed testing on the microgrid control system's logic. This testing confirmed the microgrid's equipment could interoperate with multiple manufacturers' equipment as well as its existing infrastructure and electrical assets by simulating the load of memorial gardens and the YMCA Aquatic Center. With plans in place to handle power redundancies while ensuring critical loads weren't affected, Norway Hydro Services were reassured that the microgrid will remain reliable when the sustained outages occurred on the main grid. So, to sum up, there will be no problem with your electricity because there are different variations of energy supply. Based on the project plans developed and agreed by the utility affiliate and the SES company, the community energy park's power is supplied by a combination of generation sources. The primary source of energy comes from two 265 kilowatts natural gas generators in combined heat and power system that provides sufficient thermal and electrical energy to effectively meet the facility's needs. As the CHP system operates, it produces electricity and the resulting heat byproduct is captured and then transferred to the facilities via water pipes. The primary use of this heat is to warm the community residents and during a severe winter weather situation. However, the heat also provides multiple other benefits to the community. Warming the aquatic center's pool, used for recreational purposes and physical therapy, as well as aiding the ice resurfacing process when the professional hockey rink at the Memorial Gardens was linked before each game. As you can see, there are multiple functions of this facility, not only to provide energy and electricity, but also to supply energy to different facilities as well. A 10 kilowatt solar flower supplement on-site generation at the community energy park and powers the new electrical vehicle recharging stations at the facilities. When extra energy is produced by the solar flower but not needed at the time, it's stored in a 250 kilowatts battery energy storage system for later use. The battery storage system's dynamic power capability overcomes limitations of the CHP system and thus allows the microgrid to black start as an island. The S&C Grid Master Microgrid Control System acts as the brain of the microgrid's operations. The community energy park's buildings draw the power needed to operate while the controller manages the power sources to ensure generation and load is balanced appropriately. Additionally, the controller continuously monitors the status of the microgrid's disturbed energy resources and assesses the microgrid's capability to operate as an island. It also monitors the health of the main grid supply and automatically triggers islanding if it senses a sustained outage. At the inception of the momentary outage, the controller supports two different responses. The controller continuously monitors whether the utilities affiliates protection devices will respond and restore power to the microgrid. If the system is ready, the controller works with fast-acting protective relays to execute a seamless and planned transfer and then immediately transition to island mode enabling the microgrid to ride through certain system events that will cause a momentary outage. Because momentary outages can trip solar panels inverters offline, it was important for this microgrid to have them. On to the next slide. The North Bay Hydro Services confirmed that with the SNC's company execution of the microgrid project, up to 87% of the electricity requirements for the community energy parks buildings can now be met by on-site generation, along with the other 55% of the park's heating needs. While the park's additional power and heating demands are supplemented by the main electrical grid, the battery energy storage system smooths fluctuations in disturbed energy resources availability to deliver full power to each facility when the main grid is unavailable. This reassured that North Bay Hydro Services successfully met its goal of developing a reliable, powered, and safe refuge for the community's residents if the main electrical grid experiences a sustained outage caused by a major winter storm. In alignment with the North Bay Hydro Services' future aspirations, the microgrid is also scalable, so generation sources can be added to support seamless power delivery when future updates are made to the building's infrastructures, their electrical assets, or the main grid. The utility affiliate was pleased that the microgrid's flexibility to adapt those enhancements successfully positions them, and the community it serves as technologically innovative examples of modern electrical resiliency. And to finish the study case, to showcase their modern approach to power delivery, North Bay Hydro Services decided to build an educational center into the community energy park, exhibiting each component of the microgrid and explaining how exactly they work. The solar flower, with panels that open and close automatically with sunlight availability, shows visitors sustainable energy capturing in action. The utility affiliate felt an educational aspect of the park was useful not only for the community members to learn how activities in their everyday lives are powered by some of the most advanced electrical technology, but also for regulators and industry professionals to see proof of how technology can be applied to resiliency. By collaborating with the SNC Electric to develop the microgrid, North Bay Hydro Services secured reliably powered facilities for thousands of North Bay community members to turn as a warm and safe refuge during a critical outage, while providing itself a forward-thinking utility affiliate that embraces technological innovation to solve reliability challenges. Moving on to case study number 2, Energy Sector Strategy, abbreviated as ESS in the Western Balkans. So we're going to do a little energy overview of the Western Balkans, and then we're going to also talk more specifically about the energy sector strategy, and then we're going to be able to answer the following questions, which are: what is the energy sector strategy for the Western Balkans? What is the energy generation capacity in the Western Balkans? What are the current official power generation plans in the region? What are alternative options for power sector development in the Western Balkan countries? And what are the possible scenarios for the power sector development? When we talk about the Western Balkans, we mean the following countries: Serbia, North Macedonia, Bosnia and Herzegovina, as well as Kosovo and Montenegro and Albania. So as you can see, on the right, we have some charts showing the primary energy supply, the current power generation mix, and the changes in thermal generation capacity over time. The first chart shows us how the different countries what is their primary energy supply. As you can see, in all countries, solid fuels are the most used. And let's begin to examine this a little more carefully. The total primary energy supply across all countries amounted to around 21.2 million tons of oil equivalency in 2016. This is an energy unit to help us compare the different usages in different countries. It is dominated by solar fuels, 64% of the total energy produced, followed by other renewables, as well as hydropower and oil. Gas plays an negligible role, the smallest role, as you can see. Serbia's energy consumption is around the half, 51% of the total energy consumption in the region, followed by Bosnia and Herzegovina. The final energy consumption for the 6 countries is 18.6 MTO, and is split across transport for about 30%, the industry 24%, and the other sectors. The total power generation capacity across the Western Balkan region is 17.6 gigawatts in 2018. Lignite capacity accounts for 48%, followed by hydro 46%, gas 4%, and fuel oil about 2%. Peak hourly load in January 2017 was 10.8 gigawatts. In July 2017, it was 8.3. Capacity in the region is aging, with little investment in new thermal or hydroelectric capacity in the last 30 years. Current capacity will therefore need to be refurbished or replaced in the coming years. This information is all summed up on the right in the different charts. Moving on, we're going to talk about the current official power generation plans, which is the development to the year 2014. Government plans anticipate peak demand for the region to grow from 10.8 gigawatts to 15.3 by the year 2040. Current government power generation plans across the Western Balkans suggest a future generation mix, which is dominated by lignite and hydro capacity. You can see all of this information once again on the right. Aging lignite capacity to be replaced. Total lignite capacity remains constant at 8.5 gigawatts until the year 2040, which is about 35% of its capacity. Hydropower resources has to be expanded from 8.2 to about 12 in 2014 with additional run-of-river plants. 50% of its capacity of the year. Non-hydro renewable targets to reach 2.8 gigawatts in 2014, or about 9% of its capacity. The focus is mainly on wind energy at 1.7 in 2014, or 7% of its capacity. Gas is only expected to play a minor role. The total cost associated with these plans could be in the region of 40 billion euros, including the cost of the greenhouse gas emissions could add an additional 20 to 40 billion. Annual greenhouse gas emissions in the period to 2040 would remain close to the current levels. And this always presented into the different charts and graphs. And now moving on to the next slide. Now we're going to talk about the different alternative options for the power sector development. Other potential power sector development options can be based around natural gas, renewables, and interconnections. Natural gas, the region currently has limited access to gas sources and associated infrastructure. However, future gas infrastructure projects are being considered for the region. You can see more information about the different infrastructure for gas proposals on the right here. You can see that there are several pipelines that are going to be created in order to provide gas to the region. The Trans-Adriatic Pipeline, aka TAP, the Ionian Adriatic Pipeline, and also there are other master plans for gas transportation in Albania, Montenegro, and Macedonia, which suggests extensive gasification of the countries. Albania-Kosovo gas pipeline, which would transport gas from the TAP. And here, this is a map with the different gas infrastructure projects. Moving on with renewable energy sources, the cost of intermittent renewable energy sources such as solar and wind have been declining. Renewables can be competitive relative to conventional sources. Illustrative scenarios based on different development options are on the next slide. I'm going to show you later. All these development options can be complemented by energy efficiency and smarter energy networks. Energy efficiency can reduce the need for new generation capacity. Moreover, a combination of energy efficiency and smarter energy networks can support the integration and intermittent renewable energy sources. Interconnections. Cross-border electricity trading within the region, as well as between the region and neighboring countries, can reduce the need for additional generation capacity and facilitate the integration of intermittent and renewables. And now here are some illustrative scenarios for the power section development. They are on the right, different charts and graphs. And here are the three illustrative scenarios for power sector development. Lignite and gas. You can replace all new lignite plants with gas and RAC, decommission of all lignite and replace with gas, and lignite RAC, maintain a small base of lignite and focus on solar and wind. This would require a significant increase in capacity. Here it is illustrated. This is for the year 2040. This is the generation supply, and it's measured in gigawatts. Moving on to the second scenario, the lowest cost scenario over the period 2018-2040 and in present value terms would be the gas and REC due to the lower capex and environmental costs. However, these numbers do not include import costs for unmet electricity demand, which is significant in the lignite REC scenario, see below. Dispatch analysis shows maintaining a lignite base and focusing on renewables expansions could lead to heavy reliance on imports outside the region, of the order of 24 gigawatts per winter day in 2040, or around 7% of the total daily demand. The risk of supply interruptions in renewables dominated systems could be mitigated with battery storage, although the current costs of battery storage are high. And all of this information, once again, is illustrated on the charts next to the text. And this sums up the two case scenarios. And I would once again like to thank you for joining us today. And if you have any questions, we will be happy to answer them.
Thank you very much for the information. It was quite useful for me.
Once again, the presentations will be uploaded, and you can also click on the link given at the